recording turned on. Okay. And let's look at the, I've already loaded that file up into SPSS. So I have the SPSS ready and running. And I'll just share that and we can move, pretty quickly through the SPSS, because if you got the tables that you needed, then you obviously use the right procedure to get there. And so I'll kind of do the procedures in the background a little bit and just have the output up so that we, kind of know what we're dealing with. And then when we switch over and start talking about ANOVA and correlations and all, then I'll go back to the data file and we'll kind of work from there a little bit more. Okay, everybody okay with that? All right, well, let's go to the data file first. So let me share that back up. Shuffle stuff around here so I can see y'all. And go back up here. All right. Obviously, the requirement for doing anything that remotely is related to the scientific method, the modern scientific method, which the two, the independent t-test is, as is also the paired t-test and the one sample t-test. All of those are like permutations of the modern scientific method. And so, when you do those things, you have to first identify the type of variables that you're dealing with and the type of variables that you need. And we talked about that last time when I very quickly went through those three different ways of doing things. And so but the first two questions of this had to do with simply means and standard deviations for each of the two pre-test measures and the three post-test measures. And if you wanted, you could have done those all at once simply by loading all of those in to the program. And so if we're going to go over here to analyze, crap. This little banner up here is always in the way. Okay. We're going to descriptives and we could load all those into the variable box, and that's what I'm going to do, which is I've got the wrong thing open.
No, I was looking, so I'm like, this isn't what I used.
Yeah, no, that's me. I guess I clicked on the wrong file when I was loading the file. Sorry about that. It's late in the day for me. Well, when I wake up, it's late in the day for me, so I have to go back and find that. All right. Yeah, I know where it's at. I know exactly where it's at. It's just a matter of getting over there.
So, Dr. But while you're pulling it up, if I'm ever frozen, I realized watching the recording last week, I was frozen for the last half of class. And so I didn't realize it until I watched the recording. And so I'm here. I want to make sure that it's like a camera check, make sure that I'm still moving on the screen.
Yeah, you're moving. You're moving. You're oh, there it is. Bingo. Okay. I don't know why I did that. I guess it's just foolish. Yeah, I've got you on the okay. So I'm now in the right one. In fact, I've got two of those up all of a sudden. I don't know what my machine's doing here. I say what my machine's doing is probably what I'm doing, but okay. All right, now we go pull that up again. That looks like the right one, doesn't it? Yeah, okay. And so we're going to analyze descriptives, and we want all the pre's in. And the post in. Now, one of the things I do not particularly care for that SPSS has changed is that they no longer give you the option of wanting of the median value. And the median value is kind of useful because it can give you a quick indication of which way, if there's a skew to the distribution. In other words, are there a lot of low values that kind of skew it low, or a lot of high values that kind of skew it high? And if you have the mean and the median, then you can figure out, you know, is this a non-normal distribution? But for some reason, SPSS decided to not include that. I always drop out minimums and maximums because they're, you know, virtually not needed. I generally keep all you need of this for this is the mean and the standard deviation, but I'm going to put in variance and standard error of the mean just because, yeah, sometimes those are useful to go to. Okay, now let me go and change the share over to the output file. Okay, and so you see, you know, which you should have seen. You've got the script file at the top, which I think I mentioned is you can pull this thing down, or you can copy it and paste it into what's called a script file or a syntax file and use it to run. So as someone mentioned last time, if you have a particular way of doing things, or you have a particular you know, routine that you're running on data, and then you're adding new data or more data or whatever, you can simply save, hang on to that script file, either in a Word document or in a syntax file or whatever, and then load it back into a syntax file that you can run off the machine and not have to go back through all the menu pull downs and all that if it gets complicated. And so for the two pretests, you've got the mean 9.79, 5.11. You have the standard deviation, which is 3.021 and 2.13. Now you may ask, what's the standard error? The standard error is basically if you had all the possible sample sizes, samples of a given size that included that variable, that would be the error, the standard error around all those possible means. And remember, all those means are distributed normally. You go back and think about the little rabbit and, you know, dragon thing. You know, the mean values of any given size of sample. If you have all those mean values and you average those, they're normally distributed, and the standard error of the mean roughly represents what would be analogous to standard deviation units, but it's just standard error of the mean based upon all possible means of any given sample. And so you can compute that and estimate it. And that's what's used on the t-test, is the standard error. What's used in terms of z-scores and things like that is the standard deviation. And so you also have the post-test means, and so you have 808, 671, post-test 3, 4402, and standard deviations 3.394, 2.636, and 6.644. So all of your answers to those first two questions could have come off of this one chart or this one table. Or you could have done, 5 tables and gotten the same information on 5 separate tables. But when you're doing descriptives, you can load all these variables in at once and have it do it. Now, if you have variables that are alphabet variables, alpha of alphanumeric, then when you ask for descriptive statistics, it simply won't provide them because it realizes that it can't do that. But if you ask for frequencies, it can provide frequencies. So sometimes instead of looking at descriptive statistics like this for numeric data, if you're dealing with alphanumeric data, then you can use frequencies to give you, distribution and numbers of occurrences of different things. And so we'll look at frequencies quite a little bit later, because once we get to looking at non-parametric outcomes like chi-square and logistic regression and things like that, we'll be dealing with working off of frequency charts or crosstabs, which is really frequency charts. Okay, so I'm assuming we're all okay there on those outcomes. All right. Minimum and maximum change scores that would define, on change 1, that would define the middle 95. Once again, we need descriptives. So I got to go back up to the other thingamabob. I'm not going to, this is, I wish I had my big old, okay. I'm back looking at the data set. Once again, I'm just grabbing change 1 and change 2 and getting standard deviation and mean. And that's all I need. Okay. So should be back. Are you seeing the outcomes of that, those descriptive statistics? Okay. So as you know, the mid 95 percentile is represented by the mean plus or minus 2 standard deviation units. And so for change 1, the mean is minus 1.71, standard deviation is 3.06, so 6 plus or minus 6. So it's a minus 7.71 and a plus 4.71, right? Is that right? 4.71, 5.71. Whatever 6 is added on to a minus 1.71.
So on this question, this is the one I had a question on with, when I went to go find the middle 95%, I basically just did what you did in your head. I computed it out and wrote it out. Is there not a table for that? Like I was trying to look and figure out something where I could analyze and it'd tell me the exact numbers instead of computing it by hand.
No, they typically don't, because they just kind of think you can figure that one
Okay.
out.
Well, I did, but
Yeah. Yeah, it would
I
be
just-
nice, I guess, but I don't even bother to
Okay.
look for anything like that. But as far as I know, there's not a quick and dirty little table that does that.
All right, thank you.
And then for change 2, it's 1.61, once again, plus or minus about 6. So it's 7.61 and minus 4.61, whatever it is, 4 or 5, I don't know. So the thing that crosses people up sometimes is that the default values on SPSS are to have the minimums and maximums. And sometimes people get crossed up and assume the minimums and maximums is probably the middle 95. No, it's got to be 2 standard deviations above, 2 standard deviations below the mean. But once again, I'm assuming there is no issue there. And I will be putting up an answer sheet on the same assessment form with the tables and things like that, so you can highlighted the answers and things, that sort of stuff. All right. Then we asked the significant difference between genders on the final post score, which is once again a independent samples t-test. And so when you go into the analyze, it's the compare means independent samples t-test. The test variable is change post 3, I'm sorry. The test variable is post 3, the grouping variable is gender. And once again, we have to define the groups, and the syntax always has to be right. And so it's a capital M for one group and a capital F for the other group. In this particular data set, it's 1 is M and 2 is F. And so you end up with the t-test charts, all 3 of them. The means, group statistics, kind of the descriptive stuff. The independent samples t-test. Once again, we first look at this Levene's and see if it's significant. In this case, it's not. So we can assume that these 2 samples appear as if they came from the same population. They had relatively similar variances and dispersions and all that sort of stuff. And then the t-value is minus 0.92, plus minus really doesn't matter. It's the size of the t-value. Degrees of freedom, 64. Each of the groups would have been n-1, and a significance level of 0.927. So there's no significant difference between males and females. And we're not worried about any effect size or anything like that, because, we don't have a significant outcome. And sometimes that's just the answer. It's not significant. So forget about it. Move on. And next question, significant between genders on the pre-1, similar, except that we are instead of post 3, we're doing pre-1. And when you go back into these procedures, if you're running the same procedure, except you're picking different variables, the table will default to the last thing that you ran. And so you don't necessarily have to go in and do all the, reset all the things. You just, in this case, we just deleted post 3 out of the test variable box and added pre-1, and you're ready to roll. And so this is, once again, the t-test. The Levines, not significant. So we know this is a equivariance is assumed. This is a strange one because there is no t-value. And there's the significance level is 1. Why would that have happened? Well, it would have happened because we matched males and females based on the pretest.
Is that because they have the same means on the pretest?
Yeah, we matched them. We basically said, okay, let's take a male that has a particular value and a female that has a particular value. And now let's take another male that has a value and a female that has the same value. And so we did a matching on the pretest, which sometimes you will do because you don't want there to be any differences on the pretest. And I thought about not doing that one, but then I thought, okay, well, that's fine. Well, it'll give me a chance to explain why that might occur. And so if you don't have any variance on the pretest, then you have excluded a lot of outside random influences that might have made them different on the pretest. And so we know they were the same value on the pretest. So any change or any difference on the post-test would be based upon what happened to them.
So are you saying that when you initially were collecting data, that these individual people were then cherry picked because they had matching scores?
Yes.
Okay.
Yeah. And we have a name for that, and it's well, don't have a very good name for that, but it's this idea of looking at propensity. What's the likelihood that a person with these scores would fall into this group or that group, male or female? And then once we identify the ones that are identical, we just use that as our sample. And we do that because, the big thing about the modern scientific method is that you're not looking at all these outside influences that may be out there that would affect or infect the experiment, that might have some idea, might affect the outcome in some way, but we're not looking at it, so we don't know. But if you start off at the beginning with groups that are perfectly matched, then you kind of feel like, okay, we've dealt with a lot of that. We've dealt with a lot of these random influences that might make these folks act differently. Not all of them, because we can only deal with those we can maybe think about. But we've kind of dealt with them a little bit. So now let's see what happens, because we know we have matched groups up front. So yeah, you'll do it on occasion, but it's not something that happens very often. And later on, we're going to talk about a more sophisticated way of doing that. It's called propensity score matching, which will be one of our last things we'll deal with. Now, the next question had to do with significant change from pre-1 to post-2. There's a couple of assumptions here. One, you have the same group that's getting pre-1, the same group that's getting post, post 2. And you also have the assumption that those two tests are similar, that they're kind of the same form, but that's a bad term. They're measuring the same thing, but they're just two parallel forms. And because of that parallel form thing, we can do a paired t-test. Now, there's another way to look at this, and we'll talk about that when we get over into ANOVA, but this is actually the best way to look at changes from pre to post, is just to use the paired t-test. And so I'm going back over to the data file, analyze, compare means, paired samples t-test. We're going from pre-1 to post-2, so I've got to get both of those in there, pre-1, post-2, and continue, and okay. And so in paired samples, we see that obviously there is a difference here. Is that significant? Well, one, we know these two things are correlated, but not significantly correlated. The mean values from pre to post, this is like what's called mean differences. And the t-distribution for pre-post for paired samples is the difference between each individual's pre minus each individual's post added up. Those differences added up, and then it works just like sum of squares, sorts of things. The significance level is 0.000, which means these are significant differences from pre to post. And so you might ask, okay, why would it go down pre to post? What if it's a measure of, and this actually is the measure of within a minute's period of time, how many seconds were students distracted? Because this actual data set was looking at different ways of teaching reading. And so in a minute's period of time, how often were these students distracted? Well, if one of the reading functions works, if the reading the reading methodology works, you would hope that their post-test score would be lower, because then they would be less distracted. They would be distracted 3 seconds less. Now, you might wonder, how do they get that distraction? Because somebody's sitting there with a flipping stopwatch or their watch, and actually when students are distracted, they're keeping track of that. How long, within a couple of random 1-minute periods, how long are they distracted? And so it's the joys of collecting that kind of data that everybody looks forward to in doing research. Sitting there looking at kids trying to figure out if they're distracted or not. So it's an interesting sort of set of data, and this is just a very small section of it pulled out from a much larger data set. Now, two-tailed, it is significantly different. They went from being distracted almost 10 seconds to being distracted almost 7 seconds within a minutes period. And then we look at this thing that's called a effect size. And for t-test, we're always looking at what's called Cohen's d, which is a way of determining how big a difference that really is. It's significant, but what does that mean? Is it something we really should pay attention to? And this point estimate thing here in Cohen's d, a value of 0.2 is a small effect. A value of about 0.5 is a moderate effect, and a value of 0.8 or higher is a high effect. And I'll try to put up that handout that's got a little bit more about Cohen's d in it. But that 0.2, 0.5, 0.8 thing, in this case, it would tell us that this is a significant growth from, or a significant change from pre to post, and it's a very significant effect size.
I have a question on this one.
Yeah.
Looking under where it says at the top, where it says paired samples correlation, and it gives you the 0.478 significance. What's the, because I guess when I made my determination of if it was significant or not, I looked at that number and not the 0.00 where it says significance two-tailed.
Yeah.
Which one, or I guess maybe, which one do you look at and why? I guess would be my.
You have to look at the significance in the t-test box.
Okay.
This tells you that. Can I come back to that when we do correlation here in a little bit?
Sure.
Yeah, because well, I tell you what, I'll do it right now because it's a good question to ask. I'm going to have to share my little stop share. I'm going to have to share my little overhead thingy and see if we can make some sense out of that. See, I need to slide y'all over here where I can see you. Okay. Did you happen to look at, any of you happen to look at the video about correlation, things like that? No, okay. Correlations basically convert a scatter plot into a single line, single straight line, and it's called a best fit line. It's also called a least squares line, depending on whether you're talking geometry or, you know, algebra or whatever. But it's a straight line that describes the best single relationship, or describes that the best description of the relationship between two variables, both continuous variables. In this case, there are two continuous variables here, pre-1 and post what? 2, okay? And so what actually is that if you think about a kind of a table across, that's not doing well, is it? Oh, like you want to see my hairy wrist. Let's see if I can get it focused down there. There we go. If you're looking at a graph, and on one side is pre-1 scores, and on the other side is post-2 scores. And for these students, these 60-some students, there would be a scatter plot in here that would represent each individual student's pre-1 score and post-2 score for each student. There'll be a dot that represents each student on that you know, scale sort of measure, Cartesian scale. I don't know how I forgot Descartes there for a second, but I couldn't remember Cartesian for a moment. Sorry about that. But a perfect relationship would be this 45-degree angle here. And that would represent as one went up, the other one went up. Now, if you divide it out and think of it another way as pre-1 and post-1, because they have different mean values. And let me go back over here. Pre-1 is 9.79, post-2 is 6.71. So the mean value here, pre-1, is 9.79, and the post 6.71. Okay, let me go back over to my thingy where I can see it. So you've got, you know what those two things are. So you know that this one line can't really adequately represent both of them because their values are so different. And so what that correlation for these two things represents is two separate lines. I'm going to draw another graph down here. In which, if we looked at scatter plot again and kind of divide it between with a difference of about 3 points between all those data points. In other words, we take the scatter plot we had before, and we take each one of those dots and we bump it up 3 points because the higher value is on the vertical axes. We end up with something like this. We end up with two lines. And the two lines would, in this case, probably look something like pre-1. If we draw a line through the bumped up score, this would be pre-1. And if we based it on the original scores, this would be, the post-2 score. And the fact that these things diverge, in other words, it gets bigger as it goes along, bigger difference between the two lines, means that they are, although they have a similar slope, similar, not exactly the same, similar slopes, they have a diverging difference between them, which means that they're probably, at least on this analysis, not significant. Now, when we do correlations, what we do with correlations is we convert all of these scores, these pre-1 and post-2 scores, we convert all those scores to standard scores, and we plot correlations based on standard scores. And so we take out the difference between the means of the two values of the two pieces of data by using standard scores. And so when we get back to correlation here in a minute, we'll go back to the one line, and we may find that that one line is highly significant, but we have standardized the actual data points so that we can fit them all on one line. And it's that standardization of data points that allows us to do what's called Pearson correlation, which is the correlation we'll talk about in a bit. But I wish they wouldn't even put the correlation table in here, because it's not the same as a Pearson correlation, because this one doesn't take into account the fact that you have two different mean values on what should be a similar test or same test.
I didn't watch the video, so I apologize, but I'm confused.
Okay, I was afraid of that.
Okay, so again, I was with you with the scatter plot and how you can create a best fit line.
Okay.
So
But
on
then
that
when I started
scatter
talking
plot,
about difference in means, it just kind of
Yeah.
got away.
but on the scatter plot, I guess I was like thinking about a scatter plot with like an X value and a Y value, and that's the same point. But on this scatter plot, you have two different sets of points, correct?
Right, and each
And-
one of those dots represents a subject.
And then you have, because they're two different groups or two different tests, in this case, you have to draw a best fit line for each set of dots, like red dots and blue dots. They each get a best
Yeah,
fit
essentially
line.
something like that. Yeah, but it doesn't work because the two scales are different. They're two different means and two different standard deviations, and so when you plot it on one one plot, it gets a little meaningless because of those two different things. And so you have to convert it to a common scale.
Okay.
And that's where those Z-scores come in handy. And the standardized scores come in handy. Remember when we talked about this, where we had, you know, an individual score minus the mean, and this was, say, well, we just generally talk at XJ minus the mean for the group, and that the J just means an individual score minus X for the group, and then we divide that by the standard deviation, and that becomes a Z-score. And so what we have done in correlation is to take these two different sets of scores, which have different means, different standard deviations, and we standardized them so that they now have the same mean, which is 0, and the same standard deviation, which is that normal standard normal curve.
So on the second graph that you drew, what would be the values of your X and your Y?
On this one,
Mm-hmm.
well, we would do two lines, one using using the mean and the standard deviation of pre-1 as our conversion. And the second line would be using the mean and the standard deviation of post-2 for our conversion. And that's why you end up with two lines. But what you can notice is that the slopes of the lines sometimes will diverge. The trend of the line will diverge. One will go up at a faster pace or a slower pace than the other. And because these two things have different slopes, because this line has one slope and this line has another slope, you really don't know much about them, except that it looks like they're sort of parallel, but they're not. And so I don't know whether they're correlated or not until I actually run the Pearson correlation, which uses the standard normal scores for each of those data points.
So the correlation takes the best fit line after you have the Z-scores and it
Right.
tests the two best fit lines to see if they're parallel.
Well, you only have one line once you've got the standard scores, because you're on the same scale.
So what's the correlation like testing, I guess, is my question.
Okay, well, we can do that right now, and I can do correlation first. Did you have any problem with the one sample T getting the answer to that? I mean, let me run that real quick, and then we'll do the whole correlation thing. We'll kind of jump right into that. Okay. I'm back over on the data set. The question was, if the national average for post 3 is 49.5, what's, how is these subjects doing? So it's post 3, I'm doing analysis, compare means, one sample t-test.
You'll need to switch your view.
Oh, where am I at? Oh, I'm over on this thingy. Sorry. I got way too much stuff going here. I tried it with 3 different screens. That didn't work any better. I was sharing across 3 screens, and you're talking about, you think I'm confused now. Wait until you saw me doing that. Okay. So I'm back over here now. Okay. So I'm wanting to know, is post 3 measure, is it different from a national average of 49.5? So I throw my post 3 in there as the test variable. Test value is 49.5, which I enter manually And okay. And so the one sample, which I need to change the share. Okay, now the one sample T has a significance level of 0.000, which tells us that it is significantly, this particular group's score was significantly different from the national average. This group score was 44.02. The national average was 49.5. So this group scored significantly lower on post-test 3 than the national average. So are we good there? Got that? Okay. All right, let me switch out of this altogether. All right. All right. Let me explain correlation. When you get to the video, you'll get a little bit better explanation. I just didn't want to duplicate that necessarily in here. And I need to. Okay. All right. Can you see the little cam thing? Yeah. Okay. Let's say we have two continuous variables, and just for the sake of argument, we'll say the SAT scores, and we want to know if they are predictive of GPA for the first year of students. And so we're wanting to know, if we know one of those, can we know the other one? Can we predict what the other one might be? Now, remember, we're going to deal with group outcomes when we're doing statistics. So we can't use this to predict any individual, but we can use it to predict, the mean of a group of individuals. And so it will predict a group, but we can't use it to predict each individual in the group. And so we always have to keep that in the back of our mind. We're talking about group outcomes here, and we can't predict individual outcomes. One way of working with this is to do a correlation in which we do the Cartesian thing. We just plot data on a curve. And so let's say we put SAT values on one and GPA on the other. And this in particular is the SAT math, maybe, portion, mathematical analysis or analytics or whatever they call it these days, basically the math portion. And which has a maximum value of 800, I think. Is that right? 800 or 600, since they read norm 800, I guess. And so on this mean here, we would have, at the axis would be 0. At the top, it would be 800, and then we would have an interval scale across here. And GPA would be down here at 0 and up here at, say, 4.0. And we'd have a axis of interval distribution along the way. Now, obviously, there are two separate scales here. And so it's really hard to plot it accurately on two different scales. We can, and we can draw a line through it, but we may not know for sure if that's exactly where the line is supposed to be, because we have these two different scales. And so one of the things to do is to convert each of these scales into z-scores. And so now we have what are basically standard normal distributions. Well, I'm going to bring this one over here on the other side. We have standard normal distributions that of z-scores now, of standard scores. And so instead of looking at raw values, raw SAT values, and raw GPAs, we are now looking at what are called standardized values. And since they're standard normal curve around the means, then we know that they have the same distribution, because standard normal curves are all exactly the same in terms of their structure. They have the mean is at 0, and standard deviation units go up and down with same amount of area between all the different standard deviation units. And we know that there's 95% in the middle, and all that sort of stuff. We know all that. And so when we plot these things, we end up with, at the mean, we would have one roughly about right there, because it would be at the midpoint of this value, midpoint of that value. And so we would have most of our plots, most of our scatter plots somewhere close to the mean, because that's the highest point on both distributions. And we'd have less and less as we go out, because these things would also be, if they were really correlated, these things also would be scattered in a normal distribution. Because now we have standardized it. What that means in terms of correlation is that if we can draw a line through that, that is the best fit line or the least squares line, then if we know one of these, or we know a new value, we know that somebody's SAT is 681, we can predict 681 would be, I don't know, out here somewhere, probably pretty high. We can use that correlation line to predict what their GPA would be. And the way we would do that is using what's called regression. Because if you have a straight line, you know the formula for a line. Y is equal to mx plus b. Y, in this case, would be GPA. M would be the slope of the curve. If we know the correlation, we can figure the slope. If we know the slope, we can figure the correlation, because they're related. And so this is slope times SAT plus the intercept point. And so that's why this is such a powerful thing, and why we standardize, because now we can predict one from the other. Now, when we do things like a t-test, are we okay here, sort of, maybe almost, kind of? Are we lost? Okay. I'm going to set this one aside for a sec. When we do, say, independent sample t-test, what we're actually doing is we're drawing a line, let's say male and female. We're drawing a line for female. And we're drawing another line for male. And the differences in the slopes tell us, really is what's telling us the significance. But this difference in slopes is also what allows us to predict the standard error of the mean, or the standard error of the difference, or whatever, because we're always basically working off of this model, this notion that if we have groups here, we can understand, you know, is this growing or shrinking, or is it parallel, or, you know, and that's how we know whether something's significant or not. Now, we don't actually do this to compute t-test, but it's the same thing. It would turn out the same way. And that's called the general linear model, which is all built around correlation. And if you know correlation, you know regression, because regression is just the formula for the line. Now, the value for this line here, the value for this line is computed. Let me kill this share. Go back over to, if I don't have somebody telling me what to do, I have to tell myself. All right, let's share. And this is up on your As You Learn site. This is the reason I don't present it as a formula first, okay? This is the actual formula for correlation, for the R, which is the correlation coefficient, the actual representative of the line. If at that 45-degree angle, which would be the perfect relationship, the two values would be going up as one goes up 1 unit, the other one goes up 1 unit. That 45-degree line would have an R value of 1. Now, R's can be negative and positive. If we started on the high side of the y-axis and drew a 45-degree line coming down to the x-axis, if that's the line that it drew, that would be a perfect negative relationship, and that'd be a -1. So all R values fall between 1 and -1. And obviously, the higher the absolute value, the more connected the two variables are. So at a value of 1, there's a perfect connection. At a value of -1, there's a perfect connection, except they're going in opposite directions. As one goes up, the other goes down on the negative side. But it's still a perfect relationship, just as one goes up, the other goes down. If you think about this little formula here, and I don't want to confuse you, but I know, you know, so I'll not delve too deeply into it. Figure that you have Y's and X's, and we have converted those Y's and X's. Let me get a marker here to work with. We've converted those Y's and X's to standard scores, and these are standard values now. If we multiply together those standard values and sum them all up and divide by, and these are equivalent of standard deviations you might think of. These are actually variances down here. This is all variances. This is like, this is the deviation from one value to the mean of X. This is the squared deviation of one value to the mean of X. And if you go back and think about that, you know, that earlier sort of description of, you know, how did we get to variance? This represents variance here. This represents just a deviation. So if we sum up all the deviations, multiply it by all the deviations on the other axes, on the other variable, and get the variances from each of those and multiply those together, take the square root of that, which basically gives us something like a standard deviation, and that gives us an R value. And if you, in the video and in the PowerPoint that I use in the video, I'll actually go through those calculations so you can actually see the calculations, see how the R value comes about. But the R value is what we use to tell us about the slopes of the lines and whether the two variables are related or not. The higher the R value, the more they are related. The lower the R value, the less they are related. And just to throw another equally messy concept in there, let's say we were, well, let me go. Back over here. I know you're loving this. Let's go back over here. And let's say this circle represents the variance on SAT math. And this circle represents the variance on GPA first year. This area in here represents what's called shared variance. And that's how much these two variables share whatever it is they're measuring with each other. And you might think of a bigger concept around this, and the bigger concept might be achievement, because both of those might be measures of achievement. SAT is not a measure of IQ, it's a measure of achievement. And GPA is a direct measure of achievement. So the reason that we might be able to use SATs to predict GPAs is because they're both measuring some sub-element of a bigger concept known as achievement, or some other concept that I don't know about. And this thing in here in the middle where they share space, that's called shared variance. To know if they're related, we use an R value, whatever the R is, whatever that value is. Let's say it's 0.8. If they have an R of 0.8, there'd obviously be a whole lot more overlap here. But let's say the R was 0.8. This overlapped area here, how big that is R squared. In this case, 0.8 would be 64% of the variation is shared.
So if we had an R value of 1, the two circles would be perfectly on top of each
They'd
other.
be on top of each other, right? Yeah, exactly. Yeah. But think, R is very susceptible to N. The bigger the number of cases, the smaller the R can be and still be significant. And if you think about a t-score and then having an effect size, a Cohen's d effect size, analogous to that, the R is, are they related? And is that significance? The R squared is sort of like an effect size in correlation. How much are they related? And it's been called lots of stuff. The R squared, sometimes it's called, in some texts, it's called the index of discrimination. There are all kinds of terms for it. But it's a percentage, it gives you a percentage of how much the two things share variances, shared variance. Now, there's a lot of concepts in there to kind of unpack. And, I always worry about putting all of that out there together because it's, there's a lot in there. And don't feel bad if you don't get all of that. Because as far as this course is concerned, I just want you to be able to compute correlation and interpret it. I don't want you to have to understand all the background, scenario behind correlation or behind t-test or behind ANOVA or any of those things.
So, in SPSS, you have the different options for, you can do correlation or you can do a regression. When would you use, I'm assuming we'll get to that. Maybe I'm jumping the gun, but when would you use each one?
Right now? Why don't we can do that with the data set you have right now. Why don't we do that right now?
And then I have another question while we're pulling that up, but multiple regression, is that more than 2 variables?
Yeah, you might think of instead of a 2-dimensional scaling, it's a 3-dimensional scaling. And so instead of a flat space, 2 lines, X and Y, you've got a Z or as many Z's as it takes, and you're in a cube. Or if it's 5, you're in a hexagon, or if it's 6, you're in a whatever. But you always need in a cube, which is 3-dimensional spacing, you need 3 data points. You need an X. It would be like Y is equal to X1 or M1X1 plus M2X2, plus still an intercept. It has to intercept at some point on an axis. And so it's like extending out the formula for a line beyond 2-dimensional space. But just think of solids, solid things. If you've got a flat 2-dimensional, then you don't need a cube or anything like that. If you have 3 dimensions, you need a cube. If you have 4 dimensions, then you need 5. No, you need 5. Yeah, you need a octagon, I guess. Not octagon, but what's 5? Hexagon, right? And, you know, so you just think of different bodies, you know, and so as you add more dimensions and like multiple regression, or later on when we talk about logistic regression, and if you want to visualize it as a solid space or a solid body, just think of you're drawing a point from each one of those and they intersect someplace in the middle of that body. And so multiple regression is just, you know, a cube. You've got 3 different variables, one you're trying to predict from the other 2, and somewhere in the middle of that body, if you know 2 of them, it'll predict what the 3rd one would be. It's where it's where the whole notion of the geodetic dome and all comes into play, because in physics they're just dividing the force across more surfaces in different planes, and so if you design them right, you can build this huge structure that really doesn't require a whole lot of support, because it has the forces are kind of equally distributed across all the different facets, all the different planes, and you can figure out which point you want it to rest on. And as long as you have a good foundation there, you're okay. And so there are Fuller's what did Buckmaster Fuller call it? My physics is getting rusty on me here. My architecture, not geodetic dome. He called it something else, but it's never mind. I'm getting off target here. Why don't we do a correlation? And I apologize for getting so far off target. We'll do this, and I think I've done enough damage for the day. We'll stop. Your task between now and next week is to try to watch that video that's up on there, which lays this out maybe when I was a little bit more coherent one day, and or at least it seemed like that day. Maybe I wasn't, but it was another class, and I thought it went pretty well. So that's the video that's up there. Let's go over here and look at the data stuff. Okay, I'm back on the data set and getting my little arrow pointy thing and getting rid of some of that. And what was it? What was the original one we were looking at? Pre-1 to post-2. Pre-1 to post-2. And so in order to do pure correlations in the pull-down menu, we have 2 different menu sets here: correlations and regression. And I don't know why they don't put them together, but they don't. And so in correlations, we're talking about bivariate because we have 2 variables, bivariate. And so a bivariate correlation between, keep forgetting, pre-1 and post-2. So we need the 2 values. Options, yeah, we'll keep some stats with us so we can kind of know what we're talking about. It's 2-tailed. We're not thinking, does it going up or going down or whatever. It's 2-tailed. And flag significant correlations. In other words, we'll just accept all the default values. Okay. Pearson is when we have a setup like this. Kendall, we're not going to talk about. Spearman is when we have rankings. Let's say you had rankings between 1 and 10 on each on 2 different scales or whatever. So you can do this with rankings too. So we'll stick with Pearson. Its official name is a Pearson product moment correlation. and that's the R value. And okay, now let me go over to the output file. And here's the output file. Pre-post, same values as before. The Pearson product moment correlation to post 2. Pearson product moment correlation to post 2 has an R value of 0.089, just like in the other set. But now we have a significance level of 0.478, just like in the other set. So it turns out that they're not significantly correlated anyhow. Even though you know, the R value is it's not that high. It's like 0.9. So they're not really correlated. And that's why they don't predict each other, while one doesn't predict the other one, because they have to be correlated to begin with. But we can trust the other correlation because this gives us exactly the same outcome. And so they're not correlated. The p-value is, our sig value is 0.478, which is means that if we drew their line on that graph, it'd be kind of almost like a straight line, more parallel to one axis than the other, because it's so small. Now, from this R value, we can calculate the slope. There is a formula to calculate the slope from that. Or I guess the better way to say that is the R value can also be derived from the slope. If we happen to know the line angle and the slope and all, actually what we're doing is we're deriving an R value from the slope of that line. Because the slope comes first, the line comes first, and then the R value is calculated based off of that slope. Let's see if we can find something in here that's actually pretty well correlated. Let me glance at these data points a little bit real quickly. Let's see if post 1 and post 2 are correlated. I'm going out on a limb here, so don't blame me if it doesn't work. Post 1, post 2. Well, no.
Can you just throw all the variables in there at the same time?
Yeah. We'll just do that. Let me.
Would that be like in ANOVA?
No.
Oh, okay.
Yeah, actually, yeah. In terms of doing the using these boxes, yeah. Like if we do a correlation, bivariate, we can throw in pre-1, pre-2, post-3. We can throw them all in there. Yeah. We can even throw, change 1 and change 2 in there. We can throw everything in there. Throw the kitchen sink in there. We don't care. And now let me go over to the go over and do another share on the output page. And so we get now, and you see, obviously this is a table that mirrors itself on a diagonal. And so whatever's going on up here in this quadrant, it's also going on down here in this quadrant. So for post two, not correlated. Post two, post one, not correlated. For post two and change two, that is correlated. See, here's post two, go across to change two, and the R value is 0.71, which is getting pretty high. And the significance level is 0.000.
Didn't we compute change two from post one and post two? So wouldn't it be correlated?
Not necessarily.
Okay.
Yeah, not necessarily. It's not a. It doesn't follow the transitive rules of algebra. No, it would not necessarily be still correlated, the two of them. And let's see, is there any, does post one? Well, post one is correlated to lots of things. Post one is correlated to pre one, it's correlated to pre two, it's correlated to post three, it's correlated to change one. So if we wanted to predict the score on, say, post three, let's say post one, post three, we could go and do that on a regression. Let me see, go back over here. Okay, I better show you that. So I'm going back over to the data set. Are you getting dizzy yet? So post one, post three, remember they were correlated. Post one, post three. And so I'm going over here, I'm going to analyze. One of my options is regression. I'm doing what's called linear regression, which is the second option down, linear regression. I want to predict, it has a dependent variable. I'm going to say I want to predict post three. That's my dependent variable. And I'm going to predict it based on post one. And okay. Now I'm going to go back to the, share the, there we go. Here's the outcome from that regression. Model summary, R squared, that's for the whole model, but here is the ANOVA. This is the ANOVA that tells you whether they're, whether the regression is significant or not. And it is. Regression is significant at 0.000. That's out of the ANOVA block. 0.000. And down
What is
here,
what is that little symbol next to the 000?
it's just saying that's the predictor.
Oh, okay.
Yeah.
Gotcha.
And the dependent variable is post three. So we're using post one to predict post three. And then the coefficients are down here. And I'm going to jot down the formula over here on my little detachment thing. So you see the unstandardized coefficient for post one. So I'm jotting it down on this piece of paper. We'll go right through it as soon as I can slide over there. Okay. I've jotted down the information from in here. And so I've jotted down the 0.920 and the 36.583. That's all I needed. And so now when I go to my little DocCam thing, this is now y is equal to mx plus b. And so this is the prediction equation for that regression. So if I had a post-1 score of 10, say, .92, that was the unstandardized coefficient, times 10, which would be the post-1 score, plus 36.58. Then I would predict the post-3 score to be 9.2 plus 36.58, which is equal to 45.78, 45.78. So for a post-1 score of 10, I would predict a post-3 score of 45.78.
Okay, so if you were shooting for something like in my data set, an NCLEX score that you have to have an 80 to pass, instead of putting in the, and I want to know what the pretest score would be where I could predict that they were going to be able to pass. I put the 80 in and then calculate X.
Yeah, exactly. You just slide the 80 in as a Y value and then work to calculate X. Using your same algebra stuff.
So do you go back and test to see how accurate your predictions were?
Remember, they're group predictions.
Okay.
And so around that prediction, around that value, is going to be a little confidence interval that's actually a normal distribution with that as its mean. So the mean value of that prediction is 45.78, but there's going to be a little confidence interval around that that will be shown in the stats. And, you know, it could be a value down here, it could be a value up there for an individual. But the best guess for a whole group of people that had a value of 10 would be 45.78. That would be the mean of that whole group. So if you wanted to know, you know, what would be a predictor of this 80 that you're talking about, yeah, you could stick the 80 in as the Y value and, you know, predict it off of any X value. And it would tell you, or it would tell you what X would predict 80, but you would always have to remember that there's a confidence interval around that 80. And that's why you can never, you know, I'm not a big proponent of exact cut scores, because I think you need to have, you know, to take into account that confidence interval that exists around that individual mean score. Because error is in everything. there's always that random error and the systemic error. And so even this predicted score value has a random error and a systemic error embedded in it. And so there will be a, you know, a normal distribution around it that will identify a confidence interval. Yeah, I was working with a school division who wanted me to, and they had a test that they were using in middle school grades to identify kids that they wanted then to screen further to see if they wanted to put them in their gifted and talented program. And so they called me in, and I'd done a lot of work with them before, and they want to know what value, you know, what would be the value that they should use for their cut score for their gifted and talented program. And so, you know, I asked them, I said, well, you want your gifted and talented program to be, you know, bright kids, right? You want to be the brightest kids. And they said, yeah. I said, okay, well, that one's simple. You just, take everybody above the 95th percentile on your test, and that's who you screen for gifted and talented. And obviously they were wanting to screen a whole lot more. They were wanting to have a whole lot more people in that they would screen for that. And so they said, well, why would you do that? And I said, well, if you want them to be exceptional and you want to use one test to measure who's exceptional as a group, at least use the 95th percentile, because by definition, that would be the group of students that we would think would have scored significantly higher than the average of other students on that test. And they didn't like that at all. And because it didn't identify enough students, it didn't justify them having a gifted and talented program, because they didn't have enough students they could really put in a gifted and talented program. And so they came back to me and they said, well, okay, we've thought about it and we realize where your logic's at here. How can we get more students into this assessment? And I said, okay, let's think of a couple of things that you want to use to predict the ones you might want to assess further. Not just the score on this test, but what other things might be predictive of them, you know, being a kid you want to put in a gifted and talented program. And I'm trying to remember what they settled on, but I think they finally settled on a recommendation scale that they had for teachers that they didn't like, because, you know, they were, you know, more likely to recommend their teacher's pets and things like that. And I said, well, let's use that plus this exam, and we'll do a, you know, multiple regression model, and we'll predict at what point will you have the N that you want to have for the program you want to run. And so we predicted the N, the number of kids that would actually have that would be predicted by those two things, and what score would predict that particular N, which I finagled it a little bit because, you know, I always want to have that confidence interval values in there. So, you know, I gave them scores that were slightly lower because I wanted that confidence interval in there. And so they ended up identifying about 15% of their students that could be assessed for gifted and talented, as opposed to about, you know, less than 5%. But that was all done off, you know, a regression, and you can, you know, you can use this lots of ways, but you always have to remember that that value has error in it and is the midpoint of a range of values, potential possible values. It has the highest probability of being the real predicted value, but it's not, there'll be a range of values in there for individuals. And so you have to take into account the range for individuals. Well, that topic wasn't on the agenda. Perhaps I should apologize, but yeah, it got me going, so that was good. Watch the video. Watch the video. Next week we'll add ANOVA. I'll put up. We'll use the same data set. Yeah, we can use the same data set as this formative piece. And I'll put up a couple of questions. I'll put up an example of ANOVA, and we just did the correlation one, but I'll put up another one for correlation and regression from that same data set. And maybe suggest, see if this, try these two things or whatever, and see if you can kind of work that through. But the video will help. I mean, the video will actually help. If you watch the video, it's already up there. Because, I'll go pretty systematically point by point through it. And didn't jump around as much as I did with this, but I was just following your questions, okay? So if you don't want me to go down dark alleys, don't ask questions that lead me down dark alleys.
When will these be posted?
Tomorrow. Yeah, I can't do it today. It'll be tomorrow. Yeah.
Do you want us to submit our assignments from today somewhere?
No, I just wanted you to do that, and I'll put up a formal answer sheet and all that just for more information. Because you can always refer back to those as we get into later assessments. And that's actually why I do those, is so you can kind of see where you are and you can refer back to what you got right, what you got wrong, go back and rerun it again, and whatever you need to do. I don't need to know what you screwed up. You just need to know what you screwed up. And then if you need an explanation, a little further explanation, give me a yell and we'll do a one-on-one. That's perfectly fine. It's getting interesting. We'll actually look at my article here sometime soon. I'll put up another couple so we can have some diversity to look at as we get into stuff. Yeah. So you okay? Everybody okay? I hope I didn't scare you all. I mean, today I just, I'm sorry. I got going and I realized I got a little too deep into the woods there a couple of times. And I apologize. But I will help you understand all of it if you want me to. You just have to ask. Okay, are we good? I'll get all this up. Yeah, give me in the morning. Well, give me until tomorrow evening to get it done, because this is my third day of classes, and by today I'm generally need a little bit more rest tomorrow morning. So it means I haven't had a glass of wine to drink all week, and this is Wednesday night, and I don't have class after tonight, so I have to have a little wine tonight. So, I'll be honest, I'm not lying to you. It's always the way it is. Oh, Michelle, you got here just in time. We're quitting. You have 2 videos to watch now. You have the one that's already up there, and you have this one. Did you get your boss squared away? No? Okay. All right. Sorry.
I got stuck in this truck since 10 a.m. this morning.
Well, you know how it goes. Well, you probably wouldn't have liked this class anyhow today. So you just get a little rest, and then you can, tomorrow, day after, you can watch the 2 videos and you'll be okay. Yeah. Take 2 and call me in a day or 2. Watch 2 and call me. All right. Okay, guys, y'all have a good evening, and I will get those things up, promise. As I say, it'll probably be tomorrow afternoon, later evening, before I get them up, because I'll have to, a couple of things I got to create for that. So it'll take a little while. Okay. So I'll see y'all later. Have a good evening. Stay safe.
I'm so sorry.
That's not a problem. Yeah.
I'm so sorry.
It's not a
everything.
problem.
So I'll watch the videos. And
have it.
I got SPSS up, but I was trying to manipulate some things. So I'm going to write some questions down
Okay.
and I'll
Yeah.
send them to you.
Yeah, and if you didn't, if after you look at the videos and think about all that, and if you need, a little bit more, give me a yell and I'll either deal it with email or we'll do a one-on-one or something like that.
Okay, that sounds
Okay.
good. And I was talking to Michelle, and I think she and I may partner up. So I was like, girl, I am lost. She's like, me too. So we're gonna get it figured out though.
Okay, I'm sure. I'll get you there. Don't worry. I'll do
Okay,
what I need to do.
you have a great rest of
All
your
right, you
evening.
too. Have a
All
good
right.
one. All right, bye-bye.